All right, in chapter 5, we're going to take a look at the elements, and specifically, we're going to start out with 5a and talk about something we call the periodic table. And the periodic table is what we use to organize all of the elements, and so we can understand sort of how they all relate to one another. So, first, let's start out with some early attempts to organize the periodic table. So we talked a little bit when we talked about the atom about the Greeks thinking that all the only elements were the four elements: water, air, fire, and earth. And we know obviously that is not the case. Sometime in the Middle Ages, we actually had the alchemists, if you remember those guys. Okay, they thought that there were some things that were pure, though they still didn't know exactly what all those things were. They may have thought like water was pure when now we know that it's made of two elements. Okay. And then moving forward in, let's see, 1793. Okay, 1793. That's when Lavoisier, our great friend, the father of modern chemistry, he actually made a list of things that couldn't be broken down. Now, his list at the time was not all correct, but he was at least on the right track. And then moving forward, if you remember what time period John Dalton was working, 1800 specifically, we'll say in 1803 is when he put his atomic model out. And then shortly after that is when he made a list of 60 elements. Now, he used some pretty complex notation, meaning he wrote them out in complicated ways, and lots of people didn't like that. They thought it was too complicated. Okay, so here's actually the periodic table of cupcakes, and we'll talk more about what it actually means to be periodic in just a little bit. Okay, so our early attempts were with the alchemists, Lavoisier, and John Dalton. Okay, so as I said, some of the problems with their organization of elements were they didn't know what all the elements were. And they still had, they included some compounds. So things that we know now can be broken down, they thought couldn't be. Whoops. COMPOUNDS, compounds. Okay. Also, back then, we didn't actually know what the atom was. Remember, John Dalton's atomic model was very rude and crude and did not have a whole lot of detail. So that is our first sort of area, okay, of history. From there, we'll go on to talk about Johann Dobereiner, okay, and Dobereiner started organizing the elements according to their atomic mass and different similar properties. Okay, and this was in 1829, so a few years after Dalton. Dobereiner came up with a method of triads. Okay, tri means three, so these were groups of three. All right, so it turns out that that didn't quite work, but what was important is that he started with atomic mass, and then he grouped them by properties. Okay. Okay, he started with atomic mass, and then he grouped them by properties. However, once we had these similar properties, more elements were being discovered that went in these groups of three, and so now they couldn't be just groups of three anymore. So more elements were discovered, and they didn't really fit into this model that he had. Okay, but the important thing is that the idea of periodicity was being developed. Okay, I'm going to pause this video and show that to you in class. So Dobereiner concepts of threes, this idea of periodicity is starting to come. Okay, periodicity. What does this mean? It means that some property, something about a substance, repeats on a regular basis. So periodically, something that happens periodically happens on a regular basis in some list or time sequence. So we saw that there was something repeating, okay, something happening when something repeated. So when some measurable property repeats. And what is it that we saw repeating? We saw that with the elements, okay, if you line up according to atomic mass, properties repeat. Okay, and when I say properties, I mean the way the chemicals react with other chemicals. So chemical properties as well as some physical properties as well. Okay. All right, so moving forward, all right, the next guy that came along was John Newlands. John Newlands, and he put forth an idea in 1864, so a little time later. He called the octave scheme. Okay, so we went from groups of 3 to groups of 8. Groups of 8, okay. So there were 7 columns, okay, of 8 elements, and he actually he was organizing by atomic mass, but people didn't like his idea because it involved relating science to music. Okay, so if you're familiar with the musical scale, an octave is one set of notes from, you know, A, B, C, D, E, F, G, and then you start over with A. Okay, so an octave is something we used in music. People thought that that was silly, and actually he stopped studying because he was sort of despondent. He was upset by people rejecting his idea. So he was both musical and scientific, and he was trying to make this connection. All right, so from there, okay, we come to who we call the father of the modern periodic table. All right, Dmitri Mendeleev. He was a Russian chemist and teacher. And the story goes he was actually trying to help his students understand the periodic table, and that's how he came up with it. And so he published his first periodic table in 1869, so not too much longer after Newlands, 1869. And we'll say that his method was, we'll call that Mendeleev's periodic law. Okay, Mendeleev's periodic law. Okay, and so let's see. In 1870, 61 elements were known about. There are now 94 that we know of. And what he did was he grouped these elements with similar properties, and he actually left gaps in places where it seemed like the difference from one mass to another was a lot, and maybe there was an element missing in there. Okay, and in fact, 5 years after he first published this, in 1875, there was an element. He had left a hole where gallium goes, and then gallium was discovered, and people were like, oh, that's interesting that he guessed that would be there, and now it actually exists. And then there was also a group that didn't really seem to fit the transition metals, but he kind of left them in, and that was another sort of insight that he had that later on was sort of explained better with something else. But it was a really, really great start. So let's see, what was Mendeleev's periodic law? This is the key here. which, sorry, here's a picture of what his table may have looked like. Obviously, this wasn't the very first one, but it shows some the elements here and then properties about the different elements. All right, so here's Mendeleev's periodic law. Okay, the properties of elements repeat, or sorry, vary with atomic mass. Okay, so here we're looking at the mass. As the mass changes, the properties vary. Okay, so if we put them in order of atomic mass, we see properties that sort of emerge that go together. All right, and as we said, let's see here. So some of the problems, okay, first of all, the atomic mass was sometimes unreliable. Okay. Ugh, my spelling here is awful today. Okay, sometimes unreliable. So they didn't actually know the atomic mass well. But he left gaps for elements that were later discovered. And that was a huge insight. Okay, that really allowed, that really is what made people pay attention to what he had to say. Okay. All right, I think that is it for Mendeleev, and he did a great work with what he had to go on. But as we discovered more about the atom and we discovered protons, then we came up with a new way to organize the elements. Okay, so we remember Ernest Rutherford. He was the guy who came up with that nuclear model. Well, Henry Moseley was one of his assistants, and in 1912, about 50 years after Mendeleev, he came up with the modern periodic law. And as you remember, okay, Rutherford came up with this idea of the proton, and so that's actually what Henry Moseley used. It's what we call the modern periodic law. Okay, the modern periodic law. And so he was an assistant, right? That's how he is considered the assistant of Ernest Rutherford, Henry Moseley, but he's given credit for developing this modern periodic law. Again, he was using X-rays, just like in the gold foil experiment, and he was actually able to count the number of protons in the nucleus. And he found that there were some issues with organizing things by mass that go away when you use the number of protons instead of mass. So he used the atomic number. Atomic number is the number of protons instead of atomic mass. So that is actually our definition for the modern periodic law, that the properties of elements vary. Now instead of with atomic mass, we're going to say with atomic number. Okay, so which is number of protons. Okay. Now, as far as we know, there aren't any problems with this one. However, we will say that the mass is still not, you can't still put them in order of mass. So, but in order of number of protons or atomic number, we do get some really predictable properties. So here is one image of our modern periodic table. We have our columns and our rows. The number here next to each element symbol is its atomic number. That's the number of protons. So you'll see they go in order here and then they jump back over. There's actually a spot here where we have a group that we write down here at the bottom, but really they get inserted right here. So you go 57, then down here to 58 and over, and then you would connect them back. But we write it like this just because it would be a really long piece of paper to have to write it all out. Okay. All right, we will pause there and I'll come back with another video to explain a little bit more about the elements.